Okay, so our next speaker, we're very excited to welcome Gen Z Anna Huang, a research scientist at Google Magenta, an adjunct professor at the University of Montreal. She's also a Canada CIFAR AI Chair at the moment. And perhaps, I mean, there are many things that we can say about Anna, but she holds this incredible record, I think. Certainly in the music community, I think very few people in the AI community can say that you develop a tool that got at least 55 million interactions in a couple of days. So people creating, harmonizing melodies with the Bach Doodle a few years back. A great demonstration, practical demonstration of some of the amazing research that Anna has been doing over the years. She completed her undergrad at USC a number of years back, then went to MIT to do her master's degree and her PhD at Harvard University, where also you started your collaboration with Google. So please join me in welcoming on the Music AI side, Dr. Anna Huang. Thank you.
Yeah, thank you, Juan, for the very kind introduction, and thank you for the organizers for having me here. It's really great to see everyone, and I think this is one of the first talks I feel like I'm giving after the pandemic to this crowd, so thank you. I'm going to do maybe a really quick sound check just to make sure we have sound. Okay, fantastic. So yeah, today I'm going to talk about a little bit like a tapas around AI for musical creativity. So music making has co-evolved with many generations of technology. And for example, starting from instrument making, new instruments and new developments in instruments enable new kinds of ways for performers to express and also for composers to write for them. And with the invention of electric and synthesizers like analog modular synthesizers, they really allowed us to expand a palette of kinds of sounds and textures and soundscapes that was possible. And also in terms of workflow with the drum machine and also the digital audio workstations, we have many different ways to structure and interact with music. So how can AI add to this process? So for me, I feel like machine learning can support musical creativity through a lot of different of these axes. For example, it can give us new functionality, new ways of interacting with music. For example, it can give us new sounds through interpolation, through tone transfer, style transfer, and also give us different ways to manipulate material that we have. And there's also other ways for us to specify music now. For example, we can do text to music, we can do sketch to music. All of these allow us to prototype and communicate music in a different way. And so then it brings us to this behavior part. Like these new tools allow for different kinds of new creative workflows and processes, new ways to explore, new ways to prototype, new ways to iterate, sometimes giving us more chance to kind of take more risks. Also, there's systems that we're building that are becoming more real-time, more adaptive, and allowing us to be in the flow. And something I'm really interested in is how this might allow us kind of new ways to communicate and collaborate, and in some ways, yeah, create new kinds of experiences around it. So first, I'm going to start with a little music game that is kind of responding to a lot of times when people ask me what do I work on, and I say kind of the more generative aspects of music, they ask me, how do you evaluate? Like, evaluation is always a top question. So here at Magenta, Ryan Louie interned with us, and we kind of asked this question, and he came up with this framework called Expressive Communication. And the idea is thinking about downstream, what might be some of the goals for people using these tools. So for example, you might be trying to write music that conveys a certain mood, conveys a certain kind of story. How does these tools help you, and in what way? So the game he came up with was kind of Alice and Bob. So you have Alice, the composer, and then Bob, the listener. Both of them are grounded by the same image. So Alice, the composer, uses some of these ML-powered tools or interfaces to compose two fragments of music to go with, to convey this image. So yeah, you can imagine if you're comparing, this is evaluation, so if you're comparing two models, you're comparing two interfaces, you're trying to figure out which of these help you more in this task. So as the composer is composing, we can ask them some subjective kind of questions about their experience. For example, how much control they feel like they have in the process, how much are they able to communicate what they want to communicate, and how easy or how hard it is for them to really evoke the imagery that was given and to be musical. And then once these compositions are done, the Bob, the listener, listens to them. He also sees the image, and then he has to evaluate, okay, how well does this music go with the image, and also how musical is it? So this is just a rough sketch here to kind of show how you can have both the composer giving some kind of evaluation of how they felt the process went, and also the listener really looking at the outcome, listening to the outcome, and evaluating it. So I'll just give you a couple of quick examples of like what people will be seeing, what people will be hearing, and how in terms of the evaluation. So here the setup was we're working with the music transformer model, and it's for kind of generating piano music. And the new interface that we were testing out is when you're curating the samples, you actually have this tree-like interface. So at any step of the way, you can choose to branch, and then you also have knobs to control, like, oh yeah, I want the music to build here, or I want it to be harmonically become like more dense or darker. So here, like this tree-like interface allows the people to kind of shape the music. So these are some examples that people created, and then the listeners had to listen to this to judge. So first one, this card, it's expressing that you're feeling stuck in this dome and being reflective and. Okay, in the next one, it's quite a contrast. It's a battle scene. Okay, the third one is a very dreamy, kind of curious exploration, peaceful. So this was before text-to-music, so people were actually just curating this, shaping it themselves. But this is to show, like, we were trying to propose this expressive communication task as a way for people to evaluate these models or interface improvements. So that was a short example about evaluation. In this talk, I'm going to cover a couple of different kind of axes in this generative space. I'm going to talk about modeling and how to make design models that can be more controllable. I'll start with a symbolic one, the Bach Doodle that Huang mentioned a bit, and then we'll go to a symbolic to audio model, kind of bridging MIDI and audio. After the modeling part, I'll talk a bit about the AI song contest, where a lot of musicians participated, and talk about some of the challenges they faced there, and some of the socio-cultural challenges around that. And I will conclude with some future directions about, I'm excited to kind of think about this human-AI co-adaptation setup, where we want agents and musicians to be able to play and improvise music together. So that's the agenda. Okay, so I'm going to go into the symbolic music modeling too first. So a lot of models are autoregressive, but a lot of times when musicians work with them, we want to be able to iterate. And the iteration process is going to be very kind of non-linear in the sense that you're going to go into this in all kinds of directions. You might have like random gaps in the music that you want the model to fill in. So how can you build, design a generative model that can support this process? So first, let's think about, we are modeling a distribution and like a joint distribution. And usually how we do it is we use the chain rule and we factorize it into a more tractable distribution. So here we're going to pick an ordering for factorizing, and usually it's the forward ordering. So this is a autoregressive model where you start from the beginning and then condition on what you've generated so far and then go forward. Another ordering you can imagine is, okay, yeah, maybe for music we want to work backwards. Like we know where we want to land and how are the different ways to approach it. Okay, so we could start with all the ways to end and then all the ways to lead up to it. So this is the backward order. In music, of course, we don't just have one stream of information, we have multiple streams of information. For example, multiple instruments playing at the same time. So how do we choose an ordering here? There's been a couple of orderings people choose. So for example, maybe a very naive one is, okay, we're going to just go voice by voice. But the challenge here is, thinking about harmony is much harder because it takes you a while to get to the next note that would have happened at the same time as when you were singing. So a more common ordering that people use is, okay, this is the grid. We're going to traverse the grid first vertically through time, in time. So within a time step, we're going to cover what's all sounding, and then we're going to progress through time. So each of those orderings kind of impose a way for the machine to come in to kind of like continue your process. And a lot of times what we want to do is more of this like multitask or all ways of infilling things. So if that's what we want to do, one way to do that is, okay, why don't we just do this random masking and then ask the model to do reconstruction? That way, we're creating the training data in a way kind of that mimics how we want to use it. So it turns out when you do that, this kind of data augmentation, under the hood, the structure or the orderings that you're imposing is, I'm going to illustrate with this short example. So say you have 3 notes, and the first one you see. So when you fill this in, what are you helping the model to learn? So actually, you're getting it to learn a conditional distribution of, given the first note, what the second note could be, which corresponds to a term in a particular ordering, which is 1, 2, 3. And you're also learning something else, which is conditioned on the first note, what the third note could be. So you're learning multiple of these conditional marginals at the same time. And the second one corresponds to a term in a different ordering, 1, 3, 2. So maybe you're beginning to see, if we do this masking in all ways, then we will get all the factors that we would need for any possible ordering that we would want. So for example here, for 1, 3, 2, you can get the first term. If everything's masked out, it just had to independently predict. And then the second term, you can get from this conditioning on the first note, and then the third one, with another kind of masking. So this is, so we kind of work through this process, and then we realize, there actually was a paper a couple years ago called Orderless NAID, which came up with, we were kind of following their discovery path, and it was great to see that this was actually something out there that people had validated. So that was the model. And we trained it on the Bach data set and represented the score as pixels. So each of the variables you see there is a pixel, and we use a convolutional neural network where it's very much like images. You have multiple channels, so RGB here becomes like soprano, alto, tenor, bass. So as you have more instruments, you can add these different channels. So that was the model that powered the Doodle. And I will show you a very quick demo. Maybe a lot of you have seen it.
All right, let's start with an E. E, do, E.
So the interaction here, we wanted it to be very guided, so it actually only uses a subset of what the model can do, which here is you put in a melody, and it's going to generate the accompaniment.
This sounds great. Now, let's click the harmonize.
So that was just
button.
a given, yeah. Maybe some of you recognize the melody.
It doesn't sound too bad, right? It sounds pretty awesome. But now, how does it sound if we play these 4 voices on a guitar?
Okay, I'm going to pause there. He's a guitarist, so he wanted to play it on his own instrument. But yeah, I'm glad it didn't sound too bad. Paul Davids, he has a very popular guitar channel that teaches guitar. And he happens to be Dutch, and my partner is Dutch, so yeah, we really enjoyed seeing this. Okay, so actually under the hood, how the generation process runs is that it does this rewriting. So it was actually doing Gibbs sampling in your browser. Initially, it's not so certain about what notes it should put on, so you see it's being very colorful. And then later on, it's going to become more and more certain, so the colors become more and more crisp, and then it's just tweaking the notes at the end. Okay, so that was one example of a construction of a symbolic model, and maybe a little bit tutorial into because music is this multi-stream of information happening at the same time. How do you approach that in terms of modeling? So now we're going to show an example of how do we bridge the symbolic and the audio world in kind of instrumental synthesis. So one exciting thing and challenge of music is that it's inherently kind of this multimodality, and different information is contained in these different modalities. So right now, for kind of a lot of symbolic to audio generation, it goes kind of right away, so you don't have a lot of chance to add in your control. And so we really wanted to propose kind of a hierarchical structure to how layers of information is added, so that the user has the chance to intervene at any of these steps and be able to kind of steer the properties of the audio. So I'm going to start with an example. So this is MIDI to audio synthesis. It's monophonic, so it's just single instruments. So yeah, you start with the score, the MIDI, and so this is one synthesis. Okay, and say I wanted to do some manipulation. Of course, I can change the notes around. So say I want it to end on a higher note. Okay, so I also want to manipulate the performance, like how the phrase was performed. What if I wanted more vibrato and also a stronger attack kind of coming down? And what if I wanted to kind of go in, kind of modify the synthesis itself kind of more low level? So for example, adding this glide going up. Okay. It seems like it wants me to do a double take every time. So. And it's adding some detuning. Okay, so that was actually a demonstration of how we can control the synthesis process with this model called MIDI-DDSP. So it affords us multiple levels of control. I'm going to play the original again. So this is just the model generating it by itself. And then the edited version that we went in and kind of moved the knobs around. So this is the original. This is the edited version. Okay, so the training data we had for this hierarchical setup was from University of Rochester URMP, and it's a recording of all these different instruments kind of recorded in an ensemble setting by university students. And let's hear the training data a little bit. Yeah, so it consists of a lot of these orchestral instruments, but in a chamber setting. Okay, so I'll go a little bit into like how we did this in terms of the modeling. So on the basis, in terms of the audio, the last stage of the audio synthesis, we're building on DDSP, which is a differentiable digital signal processing unit for us to be able to, you give it audio, it can do auto-encoding and extract the synthesis parameters. And then later on, when you want to play this instrument, all the user has to do is to provide a pitch contour and an amplitude contour. And then this DDSP unit already had learned how to synthesize this into audio. So for us, we don't directly have the pitch contour because we only have the MIDI, which is really straight lines. And how do you be able to generate these expressive wiggly lines? So the original application of DDSP is that a live performer can be playing. So a lot of the expressive performance features is extracted from the live performance or from a recording. But in this case, we only have the symbolic input. So how do you turn from the symbolic input into expressive performance features? So that's what we needed to model. Okay, so we have the score and we have the audio. So for each of the notes, we extract from the audio, what are the expression features? So for example, like what is the volume level? What is the vibrato? Some of these come from more of the spectral features. And with that, we can have a mapping between like, okay, the notes and the expression. And we also just scale all of these to 0 to 1 because later on, these are the sliders that people will be using to control and tweak the performance. Okay, so given the note sequence, we train an autoregressive prior to generate the expression controls. So at each step, it's going to say, yeah, for each of these features, volume, vibrato, what are the values? And conditioned on these are the expressive values for the next step, given this note, what is going to be the next set of values. And then given the note and kind of this high-level note expression values, we then generate the synthesis parameters. The synthesis parameters include the pitch contour, which is because yeah, it's a very autoregressive kind of process. So that's what we did to get the precision. And then there's the more spectrogram-based features. There we used again as a discriminator to make sure the spectrogram was actually really sharp. So yeah, it's this combo to kind of get at different parts of the sound. So with that, once we have all these features, then we're able to use the original DDSP and synthesize the audio. So here, I did this kind of pairing of the Doodle and in this MIDI to DDSP synthesis model. So we're going to start with a melody input, and then we're going to go through these two models to synthesize the audio. So first, so this is if you're literally kind of playing back the score. So then we use the Bach Doodle model to generate the other parts, and then used different instruments to MIDI-DDSP instruments to synthesize the audio for each of those parts. And this is the quartet you hear. Okay, so that was bringing us from MIDI to audio. Okay, so that was some examples of modeling and how to design models to allow for more interaction and control of the generative process. So next up, I'm going to briefly introduce the AI song contest and talk about an entry. So the AI song contest, we started it in 2020, actually at one of the Izmirs that was in Delft. And the idea is we really want to bring musicians and scientists together to explore how can these AI tools really, how can they contribute to a real life kind of musician creative process kind of into that workflow? In what ways can it extend the expression and kind of figure out, yeah, what are these new modes of human AI collaboration? So there's a few of us from ethnomusicology, from the industry in music, AI-driven music composition and computational musicology. We kind of came together to organize this contest, and it started out kind of with the Eurovision model, and now it's this international contest that people from all parts of the world can participate. It's been growing, which is really exciting. I think a lot of musicians and also researchers come to this contest in some ways to do research into understanding how these models can be relevant for artistic kind of practice. So they come not just to want to make a song, but to ask, like, what is possible? This is to show kind of a quick screenshot of the schematics in terms of the workflow that people had. And as you can see, it involves many, many different components and many modules. A lot of times people, like the teams, use 5 to 7 models to really have really fine-grained control for each of the components of the song. The reason why, so our contest is a process-driven contest, which means we really want to understand how songs and like with what was the artistic motivation behind it, this larger context and also the process itself. We want to be able to understand it in order to evaluate the song. So we actually have this template of questions that we prompt the teams to write about their the kind of the details and the anecdotes of how their collaboration went. So we're evaluating the song itself, of course, but also aspects of the workflow, the collaboration, how they thought about using the tools to extend what they were previously possible to do, and also ethical and cultural considerations around it. So here I'll show you one of the entries, which the team kind of encountered multiple facets of challenges. So first, because we're working with AI, this team wanted to really explore, like, can we use AI to express emotion? And in particular, can we use AI to express very kind of specific, vague, abstract emotions that are very culturally grounded? So Han, in this case. So immediately, one challenge that they faced was a lot of the pre-trained models that was out there at the time was trained on Western pop music. So when they used it, they didn't feel like it embodied the sentiments that they wanted. So so one of the early things that you had to do is to build a data set that they felt embodied this emotion. And of course, this is a very abstract concept. so they actually had to host a community kind of listening sessions and to kind of cross-listen, like, oh, do you hear Han in this piece? What is your definition of it? What made you feel that was conveyed? So they had to kind of calibrate among the communities to figure out what made sense and what would be helpful. Because, yeah, there was no established definition of how it sounded like. So yeah, they relied a lot on human subjective judgment about these different aspects in terms of the instruments, the sources, and the sound. So I'll play you a quick snippet of it. So this piece was co-created in the sense that there was some material that they generated, and then they arranged it, and both like in terms of the song and also the production a lot. So this leads me to the next little kind of preview, which is I'm working with a student who is also herself a musician in Indian classical music, and she's a vocalist. And she's interested in exploring how we can use interactive generative systems in her musical practice. And with some of the tools that she initially tested out and kind of tried to do a duet with, she found it pretty challenging because, of course, the models are not yet kind of thinking about the musical context in terms of like when should the models come in. For example, she felt interrupted a lot because usually in the genres that she would participate in, there was a clear structure of like when people would come in, and also more of like the vocalist and then another instrumentalist, maybe like shadowing what she's doing. So in terms of thinking about accompaniment, or thinking about the role of the generative system, like what is the relationship between the musician and the generative system? For example, yeah, is it accompaniment, or is it more shadowing, or does she want to do a call and response? So all of these kind of relationship questions we're trying to figure out. And if folks are kind of also working on some of these kind of traditions that kind of require us to rethink how the generative tools come in, I would love to chat more. Okay, so I'll wrap up in a couple of minutes by talking about some future directions. In general, I'm really interested in designing interactive generative systems that musicians can really jam with and shape and kind of negotiate that relationship. So this is a kind of aspirational example from a friend of mine. So he wanted to jam with Music Transformer, but Music Transformer is not exactly jammable yet. But he kind of created this this Wizard and the Oz setup where he pre-curated a sample and then played on top of it. So I'll just play you how this looks like. So he's using a player piano, a disc clavier, and what the model is generating is fed through the piano, so it's being played, and then he's playing on top to jam with it. So there's many challenges with this process because, for example, Pablo is doing the adaptation here. The model is not listening to him, but instead he's trying to make it work. And also it's hard for him to anticipate what's going to happen. And in terms of, yeah, him being able to steer the process and like what kind of controls are needed, they're all not there yet. So I'm going to go into that a little bit. First, I wanted to kind of introduce the model, Music Transformer, through this visualization that shows you a little bit of the inner workings of it. And the reason for showing this is I feel like there's a lot of potential through maybe some of these visualizations to help musicians understand how the model is listening, what is it listening to, and is there some way to, this kind of mental model, this kind of understanding could actually help the musician to engage in a dialogue with it. So what we're seeing here is a sample from the model just kind of playing by itself. And the exciting thing when I was working with this model is that at some point it started picking up these it was able to generate music with these compelling structures that like motifs would actually come back in a way that it felt like it was building on the previous instances. So here I'm highlighting all the places that this tremolo motif comes in. And so I was curious, how is it able to do this? We have some intuition about, with self-attention, you can really look into the past so you can see the parts that are relevant. But yeah, it was really good in looking back and finding the relevant parts. So it's not just the most recent thing that's looking the most, but it's able to jump over and reach back to the parts that were actually similar. So I'll show you a video, which is an animation of how the model is looking back as it's generating. I think the sound is a little bit soft. Maybe I can turn it up. It's great. I've heard this many times, so this time it's different. Hope you see felt like there was some shaping and it felt like it was going somewhere. Okay, so in order to have this kind of jamming set up, and we really need to support human AI co-adaptation, and this requires a two-way feedback and two-way communication. So for example, we want the model to give feedback to the user. So we talk about kind of human feedback a lot, like kind of learning from human feedback, but we actually also want the other side, which is how can the model give feedback to the user, and how can it be given in a way that feels more gestalt? So maybe the performer is actually performing, and how do you take a glance and have an idea of the overall kind of inclination of where the model is going? So for example, maybe Pablo is the pianist and my collaborator, and maybe some questions he's asking is like, which part of what I'm playing is the model listening to. So it's a little bit around kind of causality, and how can I steer the model behavior by maybe playing slightly differently, even playing a little bit softer, a little bit louder, that could affect how the model is responding. And also, how can we anticipate what is coming? So I'm interested in kind of this interpretability for supporting this kind of, in the context of co-adaptation. And I also think this being able to jam with kind of an agent can also be really interesting in music education. So instead of practicing alone, you can actually jam with an agent. And what's really cool about that, I think, is like you're practicing improvisation as communication. So you're constantly actively thinking about communication, like how is what I'm going to play impact the other agent. And it's also interesting to think about, what are the various ways that humans can give feedback in this performance setting? Some of it might be behavioral, some of it might be we have these tools and pedals and we're manipulating them as we're performing, and how does this give contextual signal to where we're going and what is a more desirable state to be in? So in terms of learning from human feedback can be very scarce. scarce. How do we get around that? And how do we think about this feedback that is kind of multi-turn, where you want to create this arc together? So two of the things, directions that we're thinking about, one is active learning. You don't need to optimize for every single case. Sometimes you're trying to perform a particular piece for a particular performance. How can you kind of optimize with respect to those goals? And also leverage uncertainty about like what areas the model is less certain about, and also give these counterfactuals of what if I try this, and maybe demonstrate, yeah, what are some ways I would respond to this. An area that I'm going into is multi-agent reinforcement learning. So kind of borrowing this framework to think about human-agent improvisation and collaboration. So how can we kind of have an environment where agents are interacting to, in some ways, simulate interaction that happens in this environment. So in some ways, it's maybe this more meta design where you're designing an environment that affects how the agents are interacting, and it might cause the different kinds of musical roles to emerge, performance roles to emerge, and different ways of coordinating and signaling. And of course, in simulation, what we discover is going to be very different from how musicians would communicate in kind of these signaling strategies between musicians. So we want to interleave the simulation process with also kind of musicians in the loop regularizing it, which then becomes additional constraints for this simulation process. Okay, yeah, so that's a little bit of a couple of examples from different areas. And I also wanted to take this opportunity to share a life update. I'm going to be moving back to Boston in the fall, so maybe if SANE is going to be in Boston next year, that's fantastic. I'm going to be starting a tenure-track position at MIT. In particular, I'm really excited because it's a shared position between computer science, electrical engineering, and music and theater arts. So it's going to be really kind of going into this interdisciplinary space with the support, the institutional support. So if you're thinking about grad school or thinking about postdocs, let me know. This is a picture from my lab at Mila that I'm going to move to MIT. And Sagiv on the left was visiting us, so we had a lunch together. Come join us in Boston. Thank you.
Thank you so much for a great talk. Questions from the audience?
Thank you for the very inspiring talk. I have a question on the a two-way AI musician feedback thing, and I guess one of the key challenges here is that AI model couldn't provide eye contact or communication back to the human, so that create an anticipation. So that for improvisation system, it's really challenging for. Basically, it's 100% human looking at the AI, trying to see what's going on, but not the other way around. Do you think there's any possibility that we can potentially solve this question?
Yeah, that's a very exciting question. So one of my collaborators on this project, he works on, Patrick Pilarski, he works on prosthetics, human prosthetics, in some kind of human robot. So we're definitely excited about kind of thinking about this more kind of embodied space where there is kind of this visual communication and yeah, kind of behavioral cues.
You're talking about the Georgia Tech, yeah?
I'm planning to visit them too, so I'm really excited. Yeah, they've been doing some, a long history of work that.
Cool. Yeah. Thank you so much.
Oh, thank you so much for the talk. I am here. Yes, about human AI co-adaptation, you write somewhere about the goal seeking and write, don't optimize for average case or full coverage, optimize with respect to goals. So first of all, could you recall the definition of average case and full coverage? What does it mean? And secondly, perhaps more importantly, what do you mean by goals? It's not obvious to me that two musicians playing together necessarily seek goals of any kind.
Yeah, thank you for the question. I think there's two parts to it. For the first part, the average versus maybe the full or the specific, I'm thinking there that, for example, maybe we have a larger pre-trained model that a lot of times, for example, when we do like text-to-music prompting, we hear, for example, if you give it like genre, instruments, it gives you a pretty kind of typical average representation of those textual descriptions. And that's really great for prototyping, and a lot of times it does have some diversity, so it's I think for the prototyping use case, that's really helpful. For us, we're thinking if what we want to do is to be able to have a performance on stage for a particular piece, we definitely want to narrow down. And in some ways, it doesn't have to be good, for example, in all genres. It just has to be good in like this one specific one, in particular, this one specific piece. But in this one specific piece, we might want very kind of specific behaviors that's kind of tuned for that performance. So that's some parts of it. There was a second part of the question. Okay. Yeah. So in some ways, I'm thinking very much like if we're composing or improvising for a particular session or piece, like we have something in mind that we're trying to arrive at. We might not know it until we kind of jam and play, and then if we arrive at it, we recognize that we're there. So yeah, a lot of this stuff would involve kind of human feedback. And
one last question.
Yeah, thanks very much. Particularly the Bach demos are the most compelling symbolic auto compositions I've heard. The only thing that ever came close in an open system was Dmitry Tomasko did some stuff at Princeton where it could go from sort of one chord to another chord in a pleasantly compelling way. So thank you so much. You had a slide where there were 5 icons, sort of, they seemed like 5 expressivity icons. One seemed like a volume, one seemed like a tremolo icon.
For the MIDI-DDSP work. To be able to steer the synthesis.
And what were those 5 parameters? Do you recall what they represented?
Yeah, there's like vibrato, there's like kind of attack. It was thinking a lot about, for example, like string instruments. And
right. And another quick question. One thing about AI music compositions when they're not accompanying, when they're coming up with symbolic, sometimes they seem like they never know when to end. Like they never know when a phrase is going to end. It's like, 30, I'll give you 32 bars and end on 32. So do you have any thoughts on how to make a phrase have this larger structure and know when to have a cadence and know when to stop other than just forcing it? Or is there any way you can think that you want to incorporate those duration constraints into the composition?
Totally. Actually, one of my first conversations with one of my current students, Nitya, was that she was proposing to solve this in her context. So in the improvisation that she does, a lot of times it's like 16 bars, but you would improvise to lead into kind of the main lead melody. So this could be like happening at measure 9. So you have like 8 measures to get into, or I guess, a number of measures, but then it has to be like 8 bars. Yeah, getting into
like an intro. Like you have to get from here to there in this many measures.
Exactly. And she says like so much of her learning with her teacher is to kind of learn ways to be able to land there in time. So we were talking about this idea of maybe using reinforcement learning, for example, to kind of like be. In some ways, this is like a goal. Like you have to land on this goal, and if you can train models to specifically to do that.
Cool, thanks. And I no longer have to learn counterpoint now, so that you've saved me, years of painful education in music theory. So thank you.
All right, let's thank our speaker once again.